So here you are on Friday morning, which means you're the most dedicated, you're really the best of the best. And I have a confession to make. The insane bit has been dialed down, because when I was compressing this talk from the 2-hour plan to the 1-hour talk, I had to sacrifice something. I may have made the wrong choice. I took out the most mind-blowing, insane parts, and I left just the practically useful parts. So that's what you're going to get. So this will be about template metaprogramming. It will not be advanced, maybe next time. It will be mainly for application programmers, for people who use some amount of template programming in their applications, but struggle to see how this metaprogramming stuff can be useful to me, and that's what I'm going to show. Library developers, A, they already know this, and B, they need a lot more precision in their metaprogramming techniques than what I'm going to show. This stuff, as I said, it's not hard, it's just useful. I will be example-driven, which means I'll show you something and I'll give you enough background to understand what it's dealing with. You know, other than what I'm still doing here, if you actually have questions, I'll be immensely gratified because it'll actually show me that I'm still teaching something to somebody. So go ahead and ask. And these are the confession parts. So as I said, insane stuff has been left out. If this is what you expected, sorry, the jet engine didn't fit into the luggage. You get something like this. It's elegant, it looks simple. There are a few tricks that you don't notice until they get you. It's not nearly as cool. So, okay, let's start from the beginning. Metaprogramming. I cribbed this from Wikipedia, I think. Writing on computer programs that write and manipulate other programs. In case of C++, it's using the template system to perform computations at compile time. What sort of computations at compile time? Why would you use metaprogramming? Move computations from just numeric computations from runtime to compile time. Generate code, usually using those compile time computations. What kind of code? Common applications are various kind of self-adapting code, or portable code, more efficient code that adapts to various environments, such as 32-bit versus 64-bit, eliminating deep runtime conditions, like in your innermost loop, if size of unsigned long equals 8, then do this, otherwise do that. Other examples. Another good one that we're actually not going to cover is, but facilitate domain-specific programming, create more expressive languages for solving specific domain problems, like state machines. Incidentally, one of those domain problems is programming in C++. It allows you to create more expressive language inside the language for expressing your programming concepts. And that's the last item. Complex software patterns can be simplified. So you'll see some of that. Let me go over the tools. Well, it's template metaprogramming. You need a template. Here is pretty much the simplest template. It's parameterized by the type, creates a constant value in C++11. You can also use static const expr. In C++03, you can use static const. You have to be careful with this. It's really easy to trigger a linker error, especially since compilers don't always implement this correctly. There are rules in C++03 about when the link error should not be triggered. They're not always followed. Now, in C++11, there is a convention that you can and should follow even if you're not using C++11. Numeric results, such as this value thing, are named value. Type results are named type. Improves readability, reusability. Okay, did I say type results? I didn't show you any type results. Well, type results are basically just like value results, only instead of enum or static const, you use typedef. And then you can query for it with : value or : type. Template arguments, not just template results, template arguments can be numbers of any integral type, bool, char, not double. Yeah, it can be char, it cannot be char star. No strings. Template specialization, that's pretty much your main tool. Here is a little struct that is char, is it a character, and most generic arbitrary types are not characters, so the value is 0. However, if the type is char, then it is char, and the value is 1. Well, that's not the only char. If a type is unsigned char, it's also char, the value is also 1. Forgetting anything? Volatile, const, unsigned, volatile, const, and unsigned, and all of that whole mix. That's actually starting to get pretty hairy. That's why we don't do this. What we do is we compose these template objects. So partial template specialization comes handy in this next example. How do I detect that a type is a const and remove the const? Well, your arbitrary generic random type is not a const. And that's a general form, unless it is a const, and that's the specialization. Don't forget volatile and const volatile. If you are using C++11 or later, you actually have that exact thing, and they didn't forget any of the volatile and const volatile. It's called remove CV. So why am I still showing you this? Actually, for the same reason why people still look at assembly code when they debug their programs. C++ compilers are very good at converting for loops in the machine code. Occasionally, you still look at the machine code. Why? Because sometimes you need to understand what's going on. Occasionally, you actually still write machine code. Why? Because you need more control than the compiler gives you. Same thing goes here. C++11 gives you all of these tools. They mostly work. Sometimes you may want to figure out exactly how they work, and sometimes you may want to actually say, it doesn't do quite what I want. I need to be able to write my own. C++11 added the type aliases that allow you to call meta functions simpler. You don't have to say : type or : value all over the place. I mean, : type, I'm sorry. Not value. Value you still have to say : type using this using template alias. You can still say : type, but you don't have to. It doesn't make the meta function itself any simpler. It makes the meta function call simpler. I don't want to have two versions of every one of my slides, so I will still type : type, but know that in C++11 you don't have to. Okay, we had some tools of metaprogramming. These are not the tools of metaprogramming. No variables, which means also no for loops. Okay, how do you do anything interesting without the for loops? You have to use recursion. So here is your most stupid recursive algorithm. Compute sum of all numbers from 1 to n by doing n plus n minus 1 plus n minus 2 and so on. Now, it's not that the template metaprogramming actually forces you to do this. It forces you to a lot of things that seem stupid. This is not one of them. Okay. Okay, well, you can still see the screens even if you can't see me. What this does is the pointer up there? Because I know the laser pointer doesn't work very well. Yeah, okay. So what this does is it says value of the sum is n plus value of the sum of n minus 1, unless, of course, it's a value of sum of 1 where we actually have to terminate and stop the recursion. Compilers do this surprisingly fast. Nonetheless, const expr functions introduced in C++11 and made better in C++14 do it much faster. If you have to do purely numeric computations at compile time, it's almost always better to do it as a const expr. If you have access to these facilities, why am I not going to be introducing const expr? Because I took all of it out. There were several good talks here about const expr. They covered it in great details. Furthermore, compilers have recursion depth limits. const_expr also has recursion depth limit. It's usually much bigger. On GCC, template recursion blows up in tens of thousands somewhere. I haven't actually figured out when const_expr recursion blows up, because I haven't got there. So first type of metaprogramming, numeric calculations at compile time. Why would you want to do that? Well, no runtime code is generated. Runtime code is bad. So compile time, what's compile time code? If this is a diesel engine, turn on low emissions. What's the runtime code? If this is a diesel engine and we're testing right now, turn on low emissions. Runtime is bad. Classic example of doing template metaprogramming calculations at compile time, computing, n factorial. I'm going to spare you that. I'll do another one that actually may be useful. Computing binary logarithm of a power of 2, which basically means if you have a number with 1-bit set, figuring out which one it is. The implementation is obvious. Shift it by 1 until you get 1, and count how many shifts. No loops. So we have to do it recursively. Recursive algorithm isn't much harder. Shift by 1 and add the number of shifts of what's left. You have to terminate when you actually get 1. Well, you wouldn't do that actually in your program. You would write something like this. This is a binary logarithm of an integer. So if you wouldn't do that to your program, why do that to your template? You can put that here. There's one slight problem. Okay, who knows what the problem is? No, the expression is correct, trust me. What's the problem? This is only true if you have 64-bit integers. Otherwise, this is not true. In particular, see that FFF000, that's the break between 32 and 64 boundary. That's not how you do it if you have 32-bit. Well, no problem. We're getting into this whole portability bit. So we create another template that is a helper template, which takes 2 template arguments, the value and let's say the size of some number that tells us whether it's 32-bit or 64-bit. So if it's 64-bit, we use the expression from the previous slide. If it's 32-bit, this is the correct expression for the 32-bit. How do we select? Well, our template metafunction log will just call the helper of the number and the size of size t. If we get 8, this result is returned here, which is on the previous slide. If we get 4, this result is returned. What happens if we get something else? It doesn't compile. Yes, undefined type. So this is actually good. We didn't provide a correct way of computing it for sizes other than 4 and 8. Maybe we should, but we didn't. Now, we don't have the for loop. We do have if then else. So how is it done? It's done like this. Again, C++11 has this very same thing as a conditional. And again, one day you may need to peek under the hood. Oh, sorry. So what does it do? Where's pointer? In general case, we return true. Now, there's no particular reason why in general true. I guess we trust people mostly at first. In the special case of n equals false, we return false as a type. You can do the same thing for numbers. Exact same thing. If specialize on the Boolean, you can specialize on true if you want. Okay, so now we can use that if to express our log2, if size of equals 8. Now we lost, of course, the third option, So we're now trusting that it's either 8 or 4, and we have to check for that somewhere else. Okay, how do we check for that somewhere else? Well, you'll see it in a moment. But we also have to check for something else. What if n is not a power of 2? That code for log 2 doesn't handle that. And you can still ask what's log 2 of the number that is not a power of 2, but you just don't get the answer the way I showed you. So the code then should not compile. Remember, these are all compile time constants. We know at compile time what n is, so we could abort compilation. Well, this is how you check for whether something is a power of 2. Everybody knows this trick? Okay. So then you can static assert on it. If you don't have C++11, you can still write your own compile time assert. In general, if you want to generate a very long, complex error message from a template, C++ compiler is your best friend, has always been. Getting error messages from templates is not hard. Okay. The big downside is C++ static assert gives you a really nice error message that actually prints that string that isn't there. The homegrown static asserts, you can add a literal that will hopefully be included in your error message, but error message is still hideous. And some compilers actually don't include the literal even if you put it in there. So some guidelines. If you need compile time numeric calculations, consider const_expr functions. If you need just a simple pre-computed value like pi, please don't write template metaprogram to compute pi. There is a way to do it as a series recursively. Just store the value. So when do you do it? You do it when it's done as a part of code generation. That's the most common use of numeric calculation. Okay, let's take a look here. We want to compute a power of x. X is arbitrary double, but the power n is integer. Well, there is no power operator, but there is a function. And that function actually takes 2 doubles. If the second one happens to be integer, you still get the correct answer. The only problem is it's actually not that efficient for large integers, because I don't know if it's special case as integer, but it doesn't do it very well, if it does. Of course, there is the metaprogramming way, which is to do it recursively. X to the power of n is x times x to the power of n minus 1. How would we write that? Well, we would write it like this. This is a meta function now, so it has to generate code. So it will generate code in the form of operator paren that returns a double, takes a double, return a double. This is runtime code, but we're generating at compile time, we're generating this series of multiplications. So x times the same thing, but with n minus 1. What is it going to actually do? What is it actually going to generate? What code? It's going to generate x times x times x times x times x n times. Why n times? Well, because when it reaches 1, it's not going to recurse, it's just going to return itself and not multiplied by anything. So if n was 2, we got x times power of 1, and power of 1 goes here, that's x, so we will get x times x. Now we also special case power of 0. Maybe you'll just call it with 0 or something. Okay, who thinks it's faster to do it by metaprogram? Faster than the POW, than the C function. No, x is double, which means it's not const_expr. So x is always double, it's not const_expr. N, however, is a const_expr. So the compiler knows what n is. The compiler doesn't know what x is. So the compiler is generating x times x times x n times. So what's faster? Just call the library, call the math library, or roll it yourself through the metaprogram? Yourself, okay. Well, the correct answer is actually measure it, which I did. So I ran this test 2 to the 27 times, just because it's a nice round number in binary. 16th power of x for random x took on my machine 9 seconds. Power of 20 took also 9 seconds. I'm sorry, there's a typo on the slide. This was 16. Power of 16 took half a second, so a little better than 10 times better, but power of 20 took 0.9 seconds. Still much faster, but it's getting slower. And the reason it's getting slower is it has more multiplications. Now, this is stupid, and as I said, well, yeah. Yes. So,
although it would be better, have you tried testing it doing this method versus using a constant expression?
okay, const expr will compile faster. Now, I'm sorry. The question was, one, wouldn't it be better to subdivide instead of multiplying 20 times? The answer is yes, and we're going to get into that. And two, wouldn't it be better to do it with a const expr expression? Now, if x is not a const expr constant, so you're not going to get this whole thing rolled into compile time, because we don't know what x is at compile time. Now, there is a kind of template const expr mixing way of generating code. It's still going to boil down to either x times x times x times x, or the binary subdivision. So at runtime, it's going to generate exact same code. Const expr will compile faster. For this one, it doesn't matter. Compilation time is so fast you don't notice it. Okay, so for example, x to the power, now subdivision, x to the power of 16 is not best computed as x times x 16 times, but x to the 8 times x to the 8, where x to the 8 is, of course, best computed as x to the 4th times x to the 4th, and so on. Okay, well, if that's what we want, that's what we write. Now, our power of n is power of n over 2 times power of n over 2, unless we have odd n. Well, no problem. For even n, we need just this. For odd n, we need to multiply it by an extra x, and this will do the integer rounded arithmetic and drop half. And of course, for n equals 0, we need to return 1. Well, let's do that. So if n modulo 2 compile time constant, we can do integer modulo at compile time as long as n is compile time constant. So if this is 1, which means it was odd, do the odd bit. If it was odd, it wasn't 0. If this is even, it could be 0, so let's check for 0. If it's not 0, do the even away, and if it's actually 0, return 1. Who thinks this compiles? Who thinks this does not compile? Well, come on, people, it's a binary question. It either compiles or it doesn't. Okay, so who thinks it compiles? Who thinks it does not compile? Who did not raise their hand? Okay, you're right. It's even worse than that. It compiles, and compiles some more, and compiles some more. And it never stops compiling unless the compiler actually has a timeout. And the reason is that even though only one branch of the question colon operator will be returned, this expression, all of it, has to be a valid expression. The compiler has to figure out that both sides are a valid expression. And the only way to figure out that a recursive thing is a valid expression is to instantiate it. And the only way to instantiate it is to go all the way down. And there is no all the way down. Well, in practice, there is a template recursion limit which you hit. The same is true for short circuit logic evaluation. Ampersand, and an or. They do what they're supposed to do in terms of logic, but they do not prevent both expressions from being evaluated. There are places in C++ where compile time errors go to hide. This is not one of them. Okay, that didn't work, so what do? We can do something like this. So of course, yeah, we need to stop the recursion with a, come on, where's the pointer? With a partial specialization, but so we write this helper class, which instead of one argument takes two. Now this is actually a very useful trick. Our problem is that we did not have a compile time const x per value, which was our terminating condition. I mean, we had it, but it wasn't explicit. We had to calculate it every time. So we couldn't specialize on it. So instead of, so now we add additional argument. Okay, now I don't have, okay, we add additional argument to the template, which is that n modulo 2. But we don't want to always calculate n modulo 2 because it's a function of n, and are we stupid? You know, if you know n, you can't figure out what n modulo 2 is. Yes, you can. So we're going to use the default template argument. We're never actually going to supply n modulo 2, but we'll always just let compiler figure it out. So now in general case, let's say general is an odd case, is an even case. A question? No, okay. Even case, if odd is true, we do the extra multiplication, and we specialize for 1 and 0. So this is a helper function. How do we call this? Here is our helper function. As I said, we don't actually have to supply the template argument. Now, notice we didn't have to supply the template argument here either. We called pow1 without the second template argument. So it's there only to give a name to this termination condition so we can partially specialize on it. That's the only purpose. It's not there because we actually want to explicitly supply it, that second argument. We never want to explicitly supply the second argument. But it's there, so we have something on which we can specialize. Partially specialize in this case. This works for any numeric expression. If you have a complex termination condition, you can add any number of template arguments that compute whatever you want to compute and terminate on any one of those. Using default arguments saves us from typing the expression on the client. What would happen if somebody tried to compute power of 5 even? That would be unusual. Yeah. Well, this faster because it actually stops compiling at some point. Oh. Well, what the compiler here will do is it will get the x to the 8 and another x to the 8 and hopefully keep them in the register and multiply them by itself. And that's what. If the compiler cooperates, you can, but the testing shows that the compiler does not cooperate. So power of 20, or actually power of 16.2 took 0.05 seconds this way, and the straightforward implementation was 0.5 seconds. So this is faster. It's 100 times faster than the C function. Okay, I'm not going to actually do these examples. I'm just going to kind of hint at what other things are possible. Pop count, the number of ones in a word. One of the faster ways of doing pop count, well, one of the fastest ways to use the SSE instructions, if you have them, but one of the faster ways that is portable across all platforms is this table-based lookup, where basically for every integer you just do a lookup, for every byte or for every short maybe, you just do a lookup in the table, and the table for every value tells you how many bits that value has. Well, somebody has to fill the table. Template metaprogram could fill that table for you. Where else do we use large static tables? CRC calculations, encryption, S matrices. They all have a formula of how they get derived. They're all derived once. Now you can do this with a metaprogram. You can do this with a const expr. As I said, this is not hard. It's practically useful. Makes your code easier to read when you actually, instead of magic numbers, have the formula. Yeah. N is integer, X is not. Of course. Well, I was raising doubles to the power of integer, so I, for integer and integer, yeah, it would be different. Since I was raising, they don't have a double integer version. Yeah. No, remember, the runtime code is still all in doubles. It's x times x times x, which is all doubles. Thank you. So the integer is the const expr or compile time constant, and it entirely disappears into the compilation bowels, and at runtime there is no trace of it other than you can count how many multiplication instructions you have. So less computation at runtime is a good thing. Okay, self-adapting code. We already had some of the self-adapting code, so let's look at another example. Bitstring. Bitstring conceptually is just a string of bits. In practice, it's implemented as an array of some underlying type. Unsigned long, int, char, one of the AVX or SSE types. And there may be reasons why you would use different base word for different string on different machines and different programs. But you still want the bit string to operate whatever your underlying integer is. Conceptually, it makes no difference. It's just how you reach for the bits. So we're going to templatize our bit string on the type t, which is some sort of integer. Here's our array of data. Now, how do we index into the bit string? Well, fortunately, all integer types have size of is a power of 2. That's a good thing. So if you have an arbitrary index, you split it, your lower bits become the index of the bit in a word, and your upper bits become the index of the word in the array. Well, for 32-bit integers, you split it bits 0 through 4 is a bit index. Okay, but how do you do it in general? I mean, what if integer is not 32-bit, but 64-bit or 256-bit? You don't want to calculate it like this every time. Everybody calculates it like this the first time. But not every time. So you write this template. As I said, these numeric calculations usually don't stand out by themselves. You embed them in your template that generates code. So remember that log2 that we did as a toy example to demonstrate partial specialization? Well, there it is. It comes in handy. As I said, size of t will be a and we have a bug in the slide. Size of t is a power of 2. Size of t plus 3 wasn't. So that code as written wasn't going to compile. It was going to assert that the number is not a power of 2. Now it will compile. Size of t is a power of 2. We need to add 3 because there are 8 bits in a byte, and we're counting bits. And size of is in bytes. Everybody will make this mistake at least once. Once you know this value of shift, which is by how much to shift the index to get rid, you shift right to get rid of the bit index and just be left with the word index. Now you still need to somehow recover the bit index. So you shift by the shift number that drops off the bit index, leaves you with the word index. Now, in order to get the bit index, you need to mask it. And you mask it with this number, which is 1, or we have to, what's a 1? 1 is an int. T may be an unsigned long. Shifting 1 as an int doesn't, you stay in an int space. So you don't, if you're doing this, you never say 1 left shift by some number, because you may need to shift by more than int has bits. Now, in T space, you are consistent. So this is your bit index. And so now you have the word, which is the index in the array, using the word index part of the index, which is the upper bits. And then we mask it with the mask, which is, what's a mask? Mask is a 1 positioned in the position of the bit index that we're looking for. So we start with a 1 like in the bit 0, and if we need to shift it, we shift it by this number. So until it's positioned right over the bits that we're looking at. We end it if the bit was set, we get true. Otherwise, we get false. There's another example. Everybody knows what DEC is. Interesting property. Question? Yeah. Interesting property of the DEC is it can grow without reallocating the memory it occupies. How the hell did they do that? They did that by using block allocation. So they have blocks of data, and they have some kind of array of pointers. Exactly how the reference structure is organized can vary, and that's not important. They have some array of pointers or some other structure of pointers. But when you need to grow a DEC, you create a new block, and you add a pointer to it. And the important part is the old blocks were never reallocated. The old data was never copied. So all your pointers to the old data and all your iterators are still valid. Very good. Now, in practice, you actually don't do like int of 1024. For memory management reasons, it's better to have not the number of data elements constant in a block, but the size of the block constant. Now, the number of the elements in the block varies, because blocks of the same size recycle better. If you saw Andre's talk on allocators yesterday, this is basically your free list allocator. When all the blocks are of the same size, they go in and out very quickly. So now the number of elements in the block is block size divided by the size of the element. Okay, how do we index into this thing? Exactly the same way. Now our index into the DEC is split into the word index and the block index. And as long as size of t is a power of 2, if it doesn't, we have to do modulo calculation. But if it does, we can use exact same technique to very quickly split the lower bits from the upper bits and compute the block index, which is, what's the block index? It's the index into this array of n star, or whatever, the t star. That's the block index, and then index of the data element within the block. Well, in this case, see, we're shifting 1 UL instead of 1, because we're operating now in size t space. If you happen to if you shift 1 and you shift it by more than 32, bad things happen. Okay, so automatic portability if you use self-adapting code in this way. Sorry? Okay. Okay, so let's do something a little more complex. Let's do some type manipulations. It kind of builds up. We keep using the previous techniques, and that's actually how all metaprogramming is. You keep composing from the things you did before until you lose track of what you've done. So type manipulation. Okay, again, start from simple. We want to know, so all type manipulations operate on types. They can return types or they can return values. Why would you return value if you operate on a type? Maybe what you want to know is the given type a pointer? Okay, that's easy. Type is not a pointer. That's simple, unless it is. And that's a specialization, partial specialization. C++11 has is pointer works exactly like this, except it also, they didn't forget like we did about const pointers and pointers to const and all that stuff. They handle all of that. Is function point, now it's actually, they didn't forget about lots of other things. Is function pointer a pointer? Is member function pointer a pointer? In the function pointer is a pointer, member function pointer is not a pointer, at least not in the is pointer sense. They have is member function pointer, which is a separate thing. So you have to, there are some non-trivial details that you have to remember. Okay. So as I said, C++11 does it for you. Const volatile stuff is a pointer, function pointer is a pointer. Now, if you need to write a meta function that is not in the library, come on, all meta functions are in the library now. The standard is complete. Why would you do anything else? Okay. Well, let's still figure out how they've done it just for historic reasons, if nothing else. Now, C++11 also has the convention they return type in addition to the value. And they have these predefined false types and true types. If you want to follow that convention in your own code and you don't have C++11, they're just structs. They have type def of themselves. They have a value of true or false. It would be a static const export in C++11. And in C++11, they have a const export operator bool. Of course, if you were in C++11, you wouldn't be re-implementing true type. Okay. Now that we know that the given type is a pointer, what does it point to? Well, here is our meta function remove pointer. This one will return a type, because it will return the type that the pointer points to. If it's not a pointer, it's not pointing to anything. So in general case, this code will not compile undefined type. If it is a pointer, then a remove ptr of u : type is the type of what the pointer points to. Again, remember const volatile and all of that. C++11 has remove ptr. It's not done quite like that. It's done with a different convention. If the type is not a pointer, removing a pointer gives you back the same type. We'll see in a moment why. If you roll your own and you don't call it remove ptr, you could do it either way, depends on what works better for you. There are good reasons to do it the way they did it. Yeah? Void is not a type, so you wouldn't get a void. I assume it would. What would happen if you stripped pointer from a void star? Void is not a type, so that's that's why they're introducing the void. But void is not a type, so I think it wouldn't compile because you cannot actually use it to declare anything. Okay, so before C++11, you had to do is a pointer, is a reference, remove reference, add const, has a member function foo all by yourself. And the compilers were not cooperating with you. In C++11, you have it all. They're called remove pointer, add const, wait a minute. They don't have that one. They do have lots of other cool things. Most of those can be implemented in C++ or 3. Things like has virtual destructor actually need compile support. It's one of the few. It looks exactly like is pointer or something like that, but that one requires a compile support. Compilers actually are getting better, and you still don't have a meta function that tells you if your object has a member function foo. So there is still some hope for me. Maybe there's something useful in some way. Okay. Why would you want to? If it's not in the C++11 headers, probably you don't need it. Well, so we covered type manipulations. Let's look at using type manipulations to generate type-dependent code. Type-dependent code is kind of similar to self-adapting code. So just like numeric calculations you were using to generate self-adapting code, you use checking type properties to generate type-dependent code, usually for efficiency. So we have this magic container of T, sometimes for correctness. So in this case, let's start with correctness. We have this magic container of T that has internal sorted order. And it sorts what it contains using operator less. Well, that's how we want it. That's how it's defined. Except if it stores pointers, sorting pointers by address value is meaningless. What we really want is to sort by what's in the object. Yeah, STL allows you to do that by using custom comparison functions. Users forget custom comparison functions. So it compiles without it. They'll run it without it, and it'll compare pointers by less. Okay, we do have isPointer. So for non-pointers, we're just going to do our sort, and somewhere inside the sort, you will have to compare two elements and swap them. So you're going to compare the two elements, and if x1 is less than x2, you'll swap it. Let's say that's the order that you want. For pointers, to the second template argument tells you whether it's a pointer or not, and it comes from this isPtr. So this is a general case. It's not a pointer, and a specialization, true, it is a pointer. We're going to compare star x, but we're going to still swap x because we are comparing what it points to, but we're swapping the data elements. Another way is a remove pointer, use remove pointer. Now we compare the result of remove pointer, but we swap the type itself. That's kind of cool. That's why remove pointer returns the type itself for non-pointers. That's really good, unless it isn't. And other examples. So let's say we have some sort that depends on which iterators you give it. Maybe you have a member function on certain type that does something faster for this type than general case, but if the type doesn't have a member function, you would do it externally. The principle is always the same. You have a check for has feature, and you have a partial specialization, true and false. If it has a feature, you instantiate one class. If it doesn't, you instantiate the other. Still, how do you test for existence of a member function? Well, okay, let's write something that calls member function sort if we have it. Otherwise, it sorts just using std sort. So now we need to have this function, meta function, has member function sort. There is a slight problem. In order to check for existence of a member function, we need to refer to its name. If that name doesn't exist, the program will not compile. We still want it to compile, we just want it to compile differently. We need some context in which compilation failures are not fatal. Standard doesn't say anything about compile. The required disclaimer, standard uses different words. It says requires diagnostic. So you can have a failure which does not require diagnostic. But basically, we need something that doesn't compile to still compile. This is where your compiler errors go to hide when they don't want to be seen. The SFINAE stands for substitution failure is not an error. Let me show you how it works. It's actually, first of all, let me tell you actually what it does. There's a lot of magic about it. It manipulates, first of all, when does it kick in? It kicks in during function overload resolution, only then. It manipulates which functions are considered valid candidates for an overload resolution. When an overload resolution takes place, the compiler generates all the possible candidates, which include non-template and template functions in whatever scopes it can reach. Now, when it considers template function, it instantiates them for the arguments that you've given. It deduces the types of arguments. If that deduction leads you to invalid expressions, that function is silently removed from the overload set and overload resolution continues. That's what SFINAE is. So let me show you how it actually, it's a very complex expression, and they changed the exact rules between C++ 03 and C++ 11, and then I think they fixed a few little corner cases later. It usually works exactly the way you want. If it doesn't, have fun figuring out why. So it's a function, it's an explicit manipulation of the function overloading set, which means we need at least two overloaded template functions. The first one will presumably contain some expression that will refer to the member function that may or may not be there. And the second one better always compile, because if they both drop out, that actually will not compile. If you're overloading, if you run out of candidates for overload resolution, that's compilation error. But we also want the first function to be selected first, as long as the expression is valid. If the expression is not valid, there is no choice. And we need to avoid evaluating those expressions, even at compile time, and we're definitely at runtime. Okay. There is a place where expressions are not evaluated, even at compile time, and that's inside the size of. So inside the size of, it's testing for being valid, but it's not evaluated. Okay, so here is has sort. This is in C++ 11. 2 template functions. We'll go through this step by step. 2 template functions with the same name. We created these 2 types for return results. Yes and no. One of them returns no. The other one actually returns yes. This is just a fancy way of saying that this function returns yes. And the reason I'm using the fancy way of saying it is because what I really want is some place to stick that expression for the address of the member function. And the place where I can stick it into is, one of the places is decal type, because decal type has the same property as the size of. This is tested for being valid expression, it's not evaluated. I don't actually want the result to be a pointer of member function, which is why I have this comma yes. The result is actually of type yes. But I want the place to put the expression in. Okay, so now has sort for something that has a member function sort compiles, and the value is 1. Has sort for something that doesn't have a member function sort compiles. Yay, the expression failure has been silenced. The result is 0. Okay, this is this is where I call the overloaded function. And I compare the return type with the return type of the good one. If I get back no, then the types are different. And how do I know that the types are different? I made the sizes different. In C++ 03, you have to have use size of to get the same result. This works in C++ 03, gives you exact same result. You just have to hide it in a size of instead of decal type. Same thing, return type is yes, expression is hidden inside the size of, otherwise exact same thing. So now we have a specialization on has member function sort. If it has, we call it. If it doesn't have, we don't call it, obviously. So we have a class no sort, and it will be sorted by cd sort. We have a class with sort, and it will be sorted by its member function sort. We have a class with some other sort. And what's going to happen to this one? This sort takes an integer. First of all, does it have a member function sort? Yes, it does. So has sort returns true. Does the code in red obj.sort paren compile? No. So this actually will go into the wrong branch and will not compile. Because what we tested for was, does it have a member function called sort? Not does it have a member function called sort of int or any particular signature. We're checking for a specific member function name, not anything else. You can use a similar technique to test for a specific member function signature. That's not a problem. The problem is, what if it also returns bool? It's probably okay to call it. You're just discarding the return value. What if it takes a long and you want to call it with int? It's a different signature. You could probably still call it with an int. So checking for a member name is too broad. Checking for a member signature is too specific. Okay, sorting processor kind of ran into trouble, but the magic container, the one that compared pointers, so that was still good. What about magic container of shared pointers? How would you like your shared pointers compared? Shared pointer is a type, it's not a pointer. Do you want to compare what it points to, or do you want to compare the 2 shared pointers themselves? You probably want to compare what it points to. What about iterators? You probably want to compare what the iterators point to, or any other pointer-like object. There are other ways to create a pointer-like object. Oh, by the way, is non-member operator star allowed? Yes. Nobody expects global operators. Okay. Well, let's skip this, but. So what we really want, okay, let's pull back. This is as close to insanity as we're going to get. What we really want is we need to know if a given expression compiles or is valid expression for whatever reason. Not that object has a member function sort, but that obj.sort paren is a valid expression somehow. Okay, I did previous one C++ 11 first. I'm going to do C++ 03 first here. This is a generic way of testing for whether a given expression compiles or not. Two template functions. This is where your expression goes. I have this convention. If you have expression of one argument, type of it will be T1. The variable of that argument will be x1. You can write any expression you want. In this case, we're just writing star x1. If star x1 is a valid expression, this will compile, and the value will be 1. If star x1 is not a valid expression, this will compile, and the value will be 0. So now, is pointer of int star is 1, is smart pointer of int star is 1, star x1 compiles. Okay, you can get this machinery from the slide. I rolled my own decal I had to because this is C++03 slide. If you were to port it to C++11, you would get rid of decal and you would use theirs. And why did I roll my own decal? Because I needed both the T1, the type, and x1, the variable. Okay, I'm going to wrap it up into, and I'm not afraid to use this word, a macro. I'm going to create a macro, define if compiles. This is how you use it. Define if compiles. Is pointer your expression of one variable? If compiles 1. 1 tells us it's one argument. Star x1. Here is your expression. This is the convention, use x1 and t1. Here is the name. This will be the name of that compile check. Oh, come on. Wait, why am I going backward? Okay, what can we do with this? Check of one argument. Can you add into it? Can you add, this checks can you add into it for any reason whatsoever? Maybe there is a global operator plus. Maybe the type is convertible to an int implicitly. Maybe it has a member function operator plus that takes an int. If for any reason x plus 1 is valid, this will compile and return true. If it's not valid, it'll compile and return false. Does it have a default constructor? Okay, there are several ways. What code do you want to compile? Maybe you want to compile new T1. If that's what you want to compile, and you branch depending on that, that's what you write. Can you assign an int to it? Go ahead and check if you can assign an int to it. You can do the same thing for two expressions, for two arguments. I mean, the same convention, T1, T2, T3, x1, x2, x3. Can you add them? If x1 plus x2 compiles, maybe you have a global operator plus. If it compiles, you get the result. So instead of testing for specific type features, okay, you can do exact same thing in C++11. You use real decal. So instead of testing for specific type features, you test for manifestations of them. Can you add these things? Let the compiler figure out how to add them, but can you add them in any way? If yes, I want to use my branch of code that adds them. If not, I have to do something else. Or maybe if not, I'll use a static assert because I want them to be addable. But I'll test not whether they have operator plus, but whether or not x plus y actually compiles. In libraries, you usually need more precise handling than that. In your practical application, daily life, this is what you normally need. You need to know whether your code would compile if you tried this expression. So this technique lets you stick basically arbitrary expression into that macro and check whether it would compile or not without blowing out the compiler. So this is the summary. Use type-dependent meta functions and partial specializations when you actually need to check for specific property. Like, is it really a pointer, meaning pointer, T star? Is it that? If you need to check whether it can be dereferenced with a star, use SFINAE principle, like this if compiles example, to check for that. Okay, and with that, we're on time. And questions, please. Yes? Crazy stuff is, as I said, it happened between the planning stage and the actual decorating stage. So no, crazy deck is not online. I never finished the crazy deck. More questions? Yes, please.
I was just checking to see if into the constant expression by declaring it a constant expression, and I think that you could, but maybe I'm just thinking that maybe my compiler is doing something different from underneath the hood, or doing the
Okay, can we still take questions? Okay. Okay. Can you assign to a const expr variable inside the const? Well, inside the const expr function, you can. I mean, you can declare the whole function to be const expr if the compiler can evaluate it. Other questions? Yes, please. Let's just go. Yeah.
Did you measure how long a particular computation took during compile time? That's what the how function?
Oh no, the results were runtime. No, those numbers were for runtime. Compile time, in general, yes, it can take longer if you go heavy on this. For this particular POW, you basically can't measure. Yes, please. Yes. Yes, there was a question there. There was any more questions? So, yes. Well, in template metaprogramming itself, you have to use recursion because you have to terminate, and that's the only way to terminate. Now, if you like, you can change it by changing the algorithm. So I've shown you this example with log2, which is normally recursive, except you can actually come up with a closed formula for a log2, and then it's non-recursive. Yeah, it's always better. Compile recursive iterations on const expr, by the way, is also better for that same reason. If you can do everything you need with the const expr. So especially at code generation, if you're just doing numerics, you can refactor it often. If you're doing code generation, you usually have no choice. You have to basically you have to terminate template expansion because things like question colon so do not terminate template expansion. So you have to terminate it somewhere, which means you have to fall back on recursion and termination. Yes. Which, of course, this cannot do. Well, C library doesn't provide it, so then the question is, if I wrote my own, I would probably write it exact same way as this metaprogram instantiates it, which is I would do divide and conquer, and it would. I didn't measure, but it would, other than the branches that it would have to take. I mean, it would have to take branches because it doesn't know what the number is. So it would have to take branches. So at the beginning it would have to, well, every time actually it would have to take branch whether it's even or odd, and then it would have to take branch whether it's zero, whether it's one or zero, or neither of those. And branches actually slower. Branches are slower than multiplication, so it'd probably still be slower, but not to the factor of 100. Yes.
So more on that. Could you use const expr to implement this so that you got both of if you do it compile time with what power you wanted?
Well, this is a power of double. Const expr will not work on doubles.
Oh
yeah. Yeah, const expr it'll refuse to operate on the. But the input value itself is not known at compile time.
No, I did that as a variable long.
Oh, okay. The reason it works is because const expr, when it cannot be const expr, silently decays into non-const expr. Okay. Any function that is declared const expr and the compiler says I can't do it is just left at runtime unless you put it in a context. Like if you try to instantiate a template with it or array, you use the result of it in an array index.
Okay, so basically it's just, you're just saying that even though it's declared as const expr, it's not really a const.
A function that is declared const expr may or may not be const expr. You can force the issue by putting the result of it into some context where const expr is required, such as square brackets. And then it will come to a head, and if it's not really a const expr, in case of square brackets, you will get a message that variable length arrays are C99 thing we don't support. Any more questions? No? Okay. Thank you.